topics so that people could relate, a little bit more about Iceland. In fact, the reason I'm doing this topic is because my dad actually worked at this plant and helped get it started in Iceland, and I had the opportunity to live there for a couple years. So it's kind of a unique plant in the fact that most of the plants that create aluminum are in the United States or select other countries. But no matter where they're located, with the exception of Iceland, the cost of creating aluminum, like the aluminum cans that we drink out of, the aluminum foil that we use, is extremely expensive, mainly due to the source of power needed to run these pot lines, which I'll explain further. A typical aluminum smelter will have anywhere around 300 pots, and these pots will produce about 125,000 tons of aluminum annually. However, the smelter in Reyðarfjörður in Iceland, called the Fjarðal project, is the whole project of building it and getting it started. It has about 336 pots, and it ends up producing 346,000 tons of aluminum per year. So what does this mean? Aluminum is formed at about 900 degrees Celsius, but once it's formed, its melting point is only 660 degrees Celsius. So some smelters use that extra heat to melt recycled metal, and therefore recycled aluminum requires only 5% of the energy required to make new aluminum. This is a little bit of a side note, but this fact is why it's so important to actually recycle aluminum cans, because once you take into account how much energy is needed to create raw alumina from bauxite to alumina to aluminum, as opposed to just melting the excess leftover scrap metal of aluminum cans, etc., is so much cheaper and so much more energy efficient. But just since we're talking about this, thought I'd throw it in there. So what happens is the aluminum smelting process is very energy intensive, as you can see, which is why, as I previously stated, most of the smelters are in areas with abundant power resources, and most of this is in remote areas, such as Iceland. And on top of this, the smelting process is continuous. Creating aluminum is a process that cannot be easily stopped and restarted, because if production is interrupted by, say, a power supply failure or something of that matter for anywhere above like 4 hours, the metal in the pots will solidify, because the in the pots are like molten, like a liquid substance, and so the metal in the pots will solidify, which requires expensive rebuilding processes, because you can't just melt it back down. Now that you have some of the basic information of, where we're starting from, how is aluminum made, what is it, what's the process, a little bit about what pots are and how much energy is used to create these pot lines and to get the aluminum started. But what is a pot line? What is, the pot, so-called, and, how does it work? Where does the cathode and anode come into play, like we've talked about in our general chemistry classes? Well, to begin, we know that alumina is reduced to aluminum metal in electrolytic cells known as pots. These pots are then organized into pot lines. Pots are organized into pot lines with an aluminum smelter. Modern pot lines have pots arranged side to side and carry out almost all maintenance using overhead multi-purpose cranes. Several tasks have to be carried out regularly, including replenishing alumina supplies, changing the anodes, and removing the finished product, which is molten aluminum metal. The molten metal is removed, or the correct lingo is tapped, from the cells and then transferred to a holding furnace prior to processing. So what is this pot that we keep talking about? A pot consists of two main parts: a block of carbon, which has been formed by baking a mixture of coke and pitch, and the block serves as this anode that we have learned about in chemistry class, which is also a positive electrode. So how does this anode come into play? So under the anode is a large rectangular steel box lined with carbon made by baking a mixture of metallurgical coke and pitch. This lining is the cathode, or negative electrode. So between the anode and the cathode is a space that's filled by the electrolyte. This mixture is then heated to about 980 degrees. The mixture is then melted and the refined alumina is added. This then dissolves in the molten electrolyte. The hot molten mixture is electrolyzed at a low voltage of 4 to 5 volts, but a high current of anywhere from 50,000 to 280,000 amperes. This process reduces the aluminum ions to produce molten aluminum metal at the cathode. Oxygen is produced at the graphite anode and will react with the carbon dioxide, or the carbon, to produce carbon dioxide, as you can see in this equation. However, some of the metal, instead of being deposited at the bottom of the cell, is dissolved into the electrolyte and reoxidized by the CO2 that has evolved at the anode. You can see in this equation. The reaction can reduce the efficiency of the cell and increase the cell's carbon consumption. So now let's break it down even further. First, we begin with the electrolyte. The electrolyte used in this process is cryolite, which is the best solvent for alumina. To improve the performance of the cells, various other compounds are added, including aluminum fluoride and calcium fluoride, which are both used because they lower the electrolyte's freezing point. The electrolyte ensures that a physical separation is maintained between the liquid aluminum at the cathode and the carbon dioxide, carbon monoxide at the anode. So now let's talk about the anode. As we have seen, the carbon anodes used in the Hall-Héroult process are consumed during electrolysis. Two designs exist for these anodes: the Soderberg and the pre-bake. Pre-bake anodes are made separately using coke particles bonded with pitch and baked in an oven. On the other hand, the pre-bake anodes are consumed and must then be changed. Soderberg anodes are baked by the heat from the electrolytic cell. They do not need to be changed but are continuously consumed. Now, lastly, let's talk about the cathode. The cathode consists of a graphite shell embedded with steel bars, which ends up minimizing the current resistance. During operation, the liquid aluminum itself begins to operate as the cathode, a feature which can complicate cell design because of the inevitable magnetic effects of such large currents. Typically, a cathode will last between 1,000 and 2,000 days before it needs replacing. Now, to finish, let's tie this into why this is important. For me in particular, I lived in Iceland and was very well a part of the building of this new smelter, and it's one of the most modern ones that is available in the world today. And I've always kind of wondered, what exactly does my dad do and what are they doing there? And he's tried to explain it to me before, and I hadn't been able to understand the complex chemistry behind it. But now that I've been through general chemistry, that whole concept of cathodes and anodes and transferring of ions and reducing from alumina to aluminum, it makes sense. And why this is applicable to anyone else is the stuff that you are learning in a general chemistry classroom, whether or not you think you will use it later in life, you never know, because everything that we do has chemistry in it. For example, my dad was an engineer, and he was environmental. When do you use chemistry? Well, this is a perfect example. And I just wanted to delve into more in depth of some of the concepts that we have been studying this semester and trying to apply them to something that I find interesting, especially with the whole thing with Iceland going on and the plant in Iceland, and just kind of bringing it all together.